Okay, let's start with 2.6, rational functions. Of course, we know that a rational number is a number that can be represented as a fraction. And so a rational function is going to be a function that is in fractional form. Okay, so we want to graph this. And in middle school, if we wanted to graph something, we would just make a table and randomly pick our, well, probably we would pick 0 and 1 and -1 for our x values. But we're not in middle school anymore, so we're going to use our brains and our knowledge from the past. And the first thing we're going to look at is this problem here in the denominator, that x plus 3 in the denominator. What do we know x plus 3 cannot equal? We know x plus 3 cannot equal 0. If I set it equal to 0 and solve for x, I see that x cannot equal -3. And what that's called, that x equal -3, that's called our vertical asymptote. That is where this function cannot go. There will not be a value for y when x equals -3. So that's the first thing we're going to do when we sketch these rational functions, is see if there are any vertical asymptotes. So x equals -3, we go to the x-axis. Oops, let's go the negative way to -3. And x equals -3 is a straight up and down line that goes through -3. There's our vertical asymptotes. That really helps. Another point that we'll want to look at is our horizontal asymptote. And so, yeah, this is not a secret because you did do this last year, but there are rules for horizontal asymptotes. If we look at this, the 2x minus 1 in the numerator and the x plus 3 in the denominator, if we start thinking about plugging in x, whether x is 1 or x is 10, we see that the denominator is only going to get so big and the numerator is going to get so big. And with the numerator is always going to be bigger than the denominator. Can you guys see that? Double a number minus 1 is going to be bigger than that number plus 3. All right, maybe not in the beginning, but as we get into the bigger numbers, this is going to be true. And so what we're going to do is we're going to remind ourselves of the rules about horizontal asymptotes. And our first rule is this. We're going to look at, in all the rules, we're going to look at the variable with the highest power. And that in the numerator is x, right, to the first power. And in the denominator, it's x to the first power. When we notice that our powers are equal, so say powers equal, question mark, then we know that we have a horizontal asymptote at the, that's equal to the ratio of the leading coefficients. So the coefficients, all right, should I have done I before E except after, probably switch E and I. It's hard to spell and talk at the same time. I may not still have that right. Anyway, so regardless, ratio of the leading coefficients, which means that when we look at this and we have it in the correct order of that a polynomial would be in, which the highest value for the exponent is first and then it decreases. We see that our leading coefficients, we have a 2 in the numerator and we have a 1 in the denominator, right? When there's nothing there, there's really a 1. So we know that we're going to have a horizontal asymptote at y equals 2. So we're going to go back to our graph and we're going to go to the y-axis. We're going to find a 2 and we're going to put in our horizontal asymptote. So the really cool thing about recognizing with rational functions that we may have a vertical asymptote. In most cases we will, and I think in all cases. I take that back, sorry, it could be a hole instead of a vertical asymptote. But once we know where our vertical asymptote and our horizontal asymptotes are, we can make a quick sketch by testing on either side of our vertical asymptote. So aren't you curious to know what happens on the left side of the vertical asymptote? Because if, depending on what we get when we plug in something to the left of the vertical asymptote, our graph could either look like this, or, let's undo that. Okay, undo that. Or it could look like this, right? So we've got to find out which side is it going to be on? Is it going to be above the horizontal asymptote or below? And the only way we can find that out is if we make a table. So I'm going to make a quick little table over here, and I'm curious to know if right here our vertical asymptote is on 1, 2, 3, -3. Let's see what happens at when x is equal to -4. When we plug in -4 in the numerator, we'll get what? -8 minus 1 is -9, and we'll get -4 plus 3, which is -1. -9 over -1 is a positive 9, and that's what we're looking for. We know that if it's at -4, it's up here, it's positive, and we know our graph looks like this. We don't have another choice. Our asymptotes with our vertical and horizontal tell us that that's the way that our graph is going to look like. This part was important because it told us our graph was on top of the horizontal asymptote versus below. And so we're going to do the same thing on the right side of the vertical asymptote. We're going to go ahead and test -2. What happens? Go back to our table, and we're going to plug in a -2. We plug in a -2, and the numerator will get what? A -5, and in the denominator we'll get a +1. So we get a -5. The number's not as important as the sign. It's negative. So on the right side of the vertical asymptote, we're going to be below the line. A -2, -5 is down here. 1, 2, 3, 4, 5. So you can use the point if you want to, but it's telling us that we're located. So let's see, -2, -5. So we're located on this side of the horizontal asymptote, and we're done. Way better than making a table like we used to in middle school. So once again, we are using vertical and horizontal asymptotes to guide us in making a quick sketch of rational functions. All right, this next one, same thing. We've got a rational function, and we're going to first look at our vertical asymptotes, any problems that may exist because we have an x in the denominator. So we're going to take our function's denominator, and set it equal to 0. We're going to factor to solve for x when the function is equal to 0, or the denominator is equal to 0, and we'll get that at x equals 3 and x equals -2, we're going to have two vertical asymptotes. So once again, when we're asked to do a sketch of a rational function, the first thing we're going to do is look at our denominator, set it equal to 0, and find out if there are any vertical asymptotes and where they exist. So what we're going to do is we're going to put the vertical asymptotes where they belong at 3 and at -2. So one here and one there. All right, let's talk about horizontal asymptotes. We reminded ourselves that if the highest power in the numerator was the same as the highest power in the denominator, that a horizontal asymptote existed at the ratio of their coefficients. So that was the first problem we did. But as we look at this problem, we see, wait a minute. We've got x to the first power over x to the second power. They're not equal. The bottom is higher than the numerator. And so the way I help my classes remember this, the horizontal asymptote, let's see. So the question is, is your function bottom heavy? Okay, if a function is bottom heavy, which means that its exponent is higher in the denominator, then we know that its horizontal asymptote is actually y equals 0. You blindly learned this last year in Algebra 2 Trig. We're reviewing it now, and then at the end of this year, when we do some calculus, we will find out the reason why this is true. We will find out the reason why, or where horizontal asymptotes come from, has to do with the end behavior of a function and the limit as x is approaching infinity. But for now, we're okay with just saying there are rules, and we're going to use them to assist us in making a sketch more easily. All right, so it's bottom heavy, the function is, and that means that there's a horizontal asymptote right there on the x-axis where y is equal to 0. So we're going to go ahead and draw this. Okay, so now we notice that we've got 3 areas to watch over, right? When we look at this first vertical asymptote at x equals -2, we know we've got to test something to the left of it to see if our function sketch lies above the horizontal asymptote or below. And then we're going to test something in between the 2 vertical asymptotes, and then we'll test something to the right of the second asymptote. And so to make it quicker, I went ahead and copied, let's see, where can I put this table and make it bigger? I went ahead and copied the table that I used, so I didn't have to remake it. So I'm going to move this. Okay. Yes, whoa. Yes, we know it's bottom heavy. Yes, we know where our horizontal asymptote is. Okay, if I make this a little bit bigger, can you guys see it? All right, so I made a table. And my table, when I plugged in -3, because right, I need to test to the left of this vertical asymptote. When I plugged in -3 into the function, I got -7.6, which told me that my graph was going to be below the horizontal asymptote. So I'm going to move my table up here. And I know that so far my sketch is something like that. And then I wanted to test what's in between my 2 vertical asymptotes. So the first one I picked was, of course, easy 0. When I plugged 0 in for x, I got that the function's value is 1/6. So I'm going to put a little dot. That's probably right about there. And so I could stop and go, oh, that means that it's like this, right? And it could be, but I have to make sure. So let me undo that because that's not going to really be right. I have to also test what's going on either side of the y-axis. So I test when x is equal to -1. When I plug x equals -1 into the function, I get 3/4. So, all right, that told me that's good. I'm probably right about here. But look what happens when I plug a 1 in. When I plug a 1 into the function, I know the function's got a lot of stuff written all over it, but if you plug 1 back into that function, you get a -1/6, which tells us we actually have something that looks like this. And that's what's going on between our 2 vertical asymptotes. And then finally, we have to see what's going on to the right of our last vertical asymptote. So I'm going to test what? 1, 2, 3. I'll test 4. Plug 4 in, I get 7/6. And that tells me, since 7/6 is positive, that I'm on this side of my horizontal asymptote. So just to review, we are setting the denominator equal to 0 and solving for x, and we know that's where our vertical asymptotes are located. Sometimes they turn out to be holes instead of vertical asymptotes, but that we will talk about in a later lesson. And then we look at the highest power in our numerator and our highest power in our denominator, and if they're equal, like the last problem, then we have a horizontal asymptote that's at the ratio of their coefficients. And if, like this one, the function is bottom heavy, that the power in the denominator is higher than the power in the numerator, then we have a horizontal asymptote at y equals 0. We use these vertical and horizontal asymptotes to help us decide which points to put into a table. So we do use a table like we did in middle school, but we're using exact points that are going to help us in our informal quick sketch of this rational function. All right, let's look at another rational function. We're going to go ahead and start the same way with our vertical asymptote. To find the vertical asymptote, we will set the denominator equal to 0 and solve for x. So it looks like we have a vertical asymptote at x equals -1. Okay, just one vertical asymptote. Then when we see when we're talking about our horizontal asymptotes, we're going to look at the power, the highest power in the numerator and the highest power in the denominator. And we're going to ask ourselves, is our function top heavy? Because if it's top heavy, we remember from last year in Algebra 2 Trig that meant there is no horizontal asymptote. And it makes sense, doesn't it? If a function is top heavy, like this function, its numerator is going to increase much more rapidly than the denominator, which means the function as a whole is increasing without bound. There's no horizontal asymptote that's going to be there stopping it's increasing or it's decreasing, depending on if we're looking at another function. The cool thing about doing calculus at the end of this year is we're going to understand so much more about horizontal asymptotes and why a function has them or why a function doesn't. So I'm looking forward to that. And I'm talking about it now because I am making this tutorial at the end of the year of 2017 where we have already done calculus, and it's been great. So I look forward to that for you guys as well. All right, but back to the problem that we're looking at. So we think, great, okay, top heavy, there's no horizontal asymptote, like, oh, that's awesome, but it's not. It's actually, oh, I put like a winky face sad. It is very sad, because before we used to have both a horizontal and a vertical, or sometimes two verticals, to guide us in how to make our table. Unfortunately, we don't have any guide except for to test to the left of -1 and to test to the right of -1, which is a pain. So I brought along my table so I didn't have to waste our precious time, our precious video time, plugging these in. Let's move the table so we can kind of see. All right. So as you can see, this part is the left side of my vertical asymptote. And I found that, let me put in some tick marks here so I can get a little bit of a sketch. But we're going to find that we're going to put a lot more things into our table than we had to before, which, you know, is unfortunate because it's time consuming, but we can do it. So -2, -4, 1, 2, 3, 4, we've got a dot there. -3, -4.5. Oh, it's heading down. -4, -5.5. Okay. And let's see, -1, 2, 3, 4, and it's going down even further. So it looks like it's doing something. And then negative, okay, I wanted to know -3.5, so -1.5, -4.5. Okay, so what it looks like it's doing, we can't really see what's going on to the very far left, but we can see that it's heading up this way, right? It's gonna be heading up that way. That's what it looks like it's doing. We could go ahead and do a -1 point. Oh no, that's not what it's doing. Okay, I'm gonna have to pause. I'm getting way too tired. Let me go back. Let me undo what I just did and let me pay attention to the points. That's what happens when you don't make a table. All right, here we go. I am just borrowing a table, so I need to pay attention. Okay, so -2, -4. Let's see. All right, sorry, I erased some of this. So -2, -4. -2, -4. 1, 2, 3, 4. Okay, I got it. -3, 1, 2, 3, -4.5. Okay, got it. Am I just going to say it's the same thing? Let's see, -4, 1, 2, 3, 4, -5 1/3. Okay, down here. Oh, I am fine. So -1.5. I am back to -4.5. Oh, okay. I was not fine at all. So let's see. Let's move the table. Okay. And trying to take a shortcut, I really kind of confused us there a little bit. So hopefully you guys see what's happening. I thought we were going this way and then shooting up towards the vertical asymptote, but we're going back down this way. Okay, that's what's happening on the left side. And on the right side, if I really pay attention and graph my points, on the right side of the vertical asymptote, when I plug 0 in for the function, I'm getting a 0. So I've got a point here. And then at -1/2, I'm 1/2. And at 1, I am 1/2. So let's see, this is interesting. 0, 0, -1/2, +1/2. 1, 1/2. I'm gonna get a few more. Let's get a few more points in here. is I'm curious to find out. See, isn't it, there's a reason why this red face is crying. It is not fun when you don't have horizontal asymptote. It makes the table job a lot harder. So let's go ahead and see what's going on with, uh, let's put one more in there. Let's put a 2. If I put a 2 in there, that's going to give me 4 over 3, because I really want to know what else is going on. So a 2, I am getting a little bit bigger, so that's 1 1/3. Okay. So what's happening is this guy's going this way, and we're going to scoop around and do something like this. Let me get rid of my table. I'm hoping that you can pause. Let's get the table in a place where we can see it. I'm hoping that you guys can pause and see that I made my table. I made 2 tables, one for the left side of the vertical asymptote, and one to the right side of the vertical asymptote. And it's not pretty, and I'll tell you why it's not pretty. Let's move this down here. It's because, and we'll learn about this later, this one actually has a slant asymptote. We can even see, right? We can see that there appears to be a slant asymptote through here. All right, if I drew it correctly, it'd look even better. We are not doing slant asymptotes until a further date, but that's why this graph looks so strange. We will, in the next section, I believe, find a better way to graph this. All right, let's please move on. This was awful. All right, so the steps. Steps to graphing a rational function. First, we're going to find the vertical asymptote by setting the denominator equal to 0. And be careful, if your function can be simplified, then one of your VAs may go away. We haven't seen that yet. We may see that in an example coming up. Then we need to move on to find the horizontal asymptotes. If your highest powers in the numerator and denominator are equal, then the horizontal asymptote is going to be equal to the ratio of their coefficients. If it's bottom heavy, then the horizontal asymptote is going to be y equals 0. And then top heavy, no horizontal asymptote. I don't have that written down, so I'll put no horizontal asymptote, frowny face. All right, so let's continue. All right, so we look at this. We're going to go ahead and set the denominator. We're going to find our vertical asymptotes. We're going to set our denominator equal to 0. We're going to factor this difference of 2 squares and set each one of these equal to 0. And we'll get that x equals -1 and x equals 1. So we think that there are 2 vertical asymptotes, but we were just given a hint in the last slide that says, be careful, you may not end up with as many vertical asymptotes as you think. So we're going to add a new step, and that is, when we're done with our vertical asymptotes, we're going to add simplify. So that means take your function and put it in its most simple terms. So when we see x plus 1 over x squared minus 1, we know that's equal to x plus 1 over x plus 1, x minus 1, and we say, oh, I have x plus 1 completely cancels out with x plus 1. So what that means, guys and girls, is that x plus 1, this whole route right here, instead of ending up with a vertical asymptote, we actually end up with a hole in the graph, okay, which is very important, but we don't end up with a vertical asymptote. So in this case, for this problem, this is the only vertical asymptote we have. So we're going to go ahead and graph that. I'm going to check on my time because I know we've been spending quite a bit of time on this. So we will put a vertical asymptote at x equals 1. And we will look out for that hole in the graph when x is equal to -1. We can't do anything about the hole in the graph yet. We need to see where the graph is, where the y value is when x is equal to -1. All right, so let's still go to horizontal asymptotes. And I'm going to do horizontal asymptotes next. I'll put them over here. The horizontal asymptote, when we're bottom, where our function is bottom heavy, it's at y equals 0. And so now we're going to make a table. Did I cheat and make a table for myself and attach it? Nope, gotta make my own table. That probably will keep me focused and it'll be a good thing. So here we go. We're going to be checking the values from the left of the vertical asymptote at x equals 1 and the right. I'm going to pick something easy for my table and I'm going to pick 0. What's going on when x is equal to 0? I'll plug 0 in. I'll get 1 in my numerator and -1 in my denominator. So I get -1. So 0, -1, I'm going to have on this side, which tells me right away, because of my horizontal asymptote and vertical asymptote, that my graph looks like this. And now I need to see what's going on the right side of my vertical asymptote. So that means I'm going to plug the number 2 in. So I'll get, what, 3 on the top, and I'll get 4 minus 1, which is 3 on the bottom. So I get a positive 1. So when I go over 2, I'll be up 1, which tells me I'm on this side of the vertical asymptote. Oh, I was almost going to go to the next slide. The whole at x equals -1. All right, so let's go to, let me put a few more tick marks in here. The whole at x equals -1. Let's see, 0, -1. What we're going to do is we're going to look at the graph and we're going to see when x is equal to -1, there should be a hole. Currently, we see a solid line. I knew that eraser was going to get rid of way too much. So let's do this. We're going to have a hole in the graph when x equals -1. So this indicates, if you look at it, that the graph is going along having values, having y values continuously throughout all the x's, and then bam, right when x is equal to -1, there is no value. There's a hole. There's no value for y. All right, applications. The Game Commission has determined that if 500 deer are introduced into a preserve, the population at any time, t in months, is given by this formula, which is a rational function, right? What's the carrying capacity of the preserve? Why don't we go ahead and write it a little differently? They're kind of trying to trick us. If we rewrite it like this, then we can see that it's a rational function with equal powers in the numerator and the denominator. So we know that our vertical asymptote, our horizontal asymptote will be 350 divided by 0.2. And we put that in the calculator. Our horizontal asymptote is going to be y equals, and I have it, I don't have a calculator, but I did copy the answer, and it looks like it's 1750. Does that look right? Yeah, 1750. Okay, what does that mean? This is pretty cool because horizontal asymptotes have to do with the end behavior of graphs, how much they're increasing, how much they're decreasing. Are they increasing without bounds, or do they have a bound placed on them, a horizontal asymptote placed on them that says, this is it, this is as big as you're going to get? Well, it makes sense that in a preservation, that we would have a limit, right? Like these game, whatever they are, the deer, couldn't populate into infinity, right? And there are going to be things that happen to these deer, and so their population is going to have a horizontal asymptote. It is going to be bounded by the laws of nature, right? And so in this case, for this preserve, the maximum amount of deer are going to be 1,750. So that's their carrying capacity. Okay, I've talked too much. This video is too long. Hopefully it was good, and I will see you in class. Thanks for joining me.